Cost-effective and accurate means of localizing mobile radio transmitters is a key enabling building block of many innovative applications, such as indoor navigation, smart home, assisted living, and augmented reality. This paper presents a single-packet, single-channel switched antenna array for RF localization that uses a high-speed RF switch that runs freely from a single receiver chain to determine the angle of arrival of individual packets. Existing phase antenna arrays use synchronized receivers to calculate the angle of arrival of an incoming RF signal. However, the cost increases drastically as the number of receivers multiplies. To address this issue, researchers use a RF switch to switch through the antennas. This approach reduces the number of receiving chain to 1, but requires special modifications on the receiver end to record the state of the switch, increasing the system's hardware complexity. In our approach, the RF switch runs freely in a predetermined switching pattern. The switch timing is recovered in the signal processing stage afterwards. Therefore, devices with just a single receiver chain can perform angle of arrival calculation without any modification. We choose BLE advertising packets broadcasted off a phone as our target signal. But before the angle of arrival calculation, the system needs to first find the packet out of the received data stream, recover the antenna labels, and align the waveform to compensate for phase drift. Here is the received signal strength of the packet from a switched antenna array. The jumps and discontinuities are created when switching from one receiving antenna to another. The discontinuity also shows in the phase derivative of the waveform, causing bit errors when decoding. Instead of decoding the bits, we match the portions in the waveform that is fixed for all packets to the incoming data stream for packet detection, and match the UUID portion from a registered list to identify which device the packet comes from. After receiving a packet, the system has to recover the switch timing to identify which antenna is used to collect which sample. Since the switch pattern is predefined, the spacing between the peaks reveals which antenna is used within which segment. Instead of matching the mask to the raw magnitude waveform, the derivative of the magnitude is used as one feature to emphasize the peaks. The peaks in the phase derivative waveform are also extracted by comparing it with the phase derivative of an ideal waveform, generated since all the bits are known. The two features are combined and then matched with the mask. The starting point of the switch pattern is found, and the antenna label of each sample can be recovered, with zero modification to the receiver. Now the samples are labeled. Calculating the phase difference of each antenna segment should reveal the angle of arrival of the signal. However, every antenna receives separate, non-overlapping segments of a packet. We can't simply subtract the phase of the antenna segments since they are not received at the same time, and the waveform is modulated with different bit sequences. Moreover, a phase drift caused by the carrier frequency offset is embedded in the received waveform as well. To overcome this issue, a virtual reference antenna constructed by an ideal packet waveform is introduced. This waveform mimics a non-switching receiver with zero phase drift. By subtracting the phase between the switched and the ideal waveform, the modulation is removed, and the slope caused by the carrier frequency offset is revealed as shown in the green line. The phase drift can be compensated by calculating the slope in each antenna segment. Thus, the phase differences across antenna pairs can be calculated without the need of actually use an extra non-switching receiver, or have special modifications to the packet, or receive the same packet multiple times. Then we can average the correct phase offset of each antenna segment and perform multi-resolution beaming that sweeps through and find the best fitted angle of arrival for the measured phase differences. Or use our modified music algorithm to calculate angle of arrival by duplicating the noise pattern onto the ideal waveform to synthesize a fully synchronized array. Here is a clip showing the system running in real time as the user moves around holding a phone. The system overlays the calculated angle of arrival onto the camera feed as shown on the TV screen. The blue dot indicates the angle of arrival of the BLE packets transmitted off the smartphone. The antenna array hardware has 8 patch antennas connected to a RF switch controlled by a free-running Teensy. The output of the RF switch is collected by Pluto SDR at 2 MHz sampling rate. The sample data stream is sent to a desktop computer via a USB cable for signal processing. We first evaluate the system in a low multipath open space lobby. For the transmitters, we use off-the-shelf phones with common BLE apps to broadcast BLE packets. We also tested the system with the phone always within the receiver's line of sight, against when the phone is carried in the user's pocket, representing a real-world use case. During the test, the user moves around in the space freely instead of standing still at certain spots. The system achieves sub 3-degree angle of arrival accuracy, and is able to locate the moving target using two arrays with 30cm localization arrow. A more complex scenario, a multipath rich office environment with desks, monitors, and chairs is evaluated as well. Moreover, the system is tested with 5 users, each with a phone in the pocket at the same time. The system performs with an angle of arrival accuracy of 5.9 degrees and a localization accuracy of 68.4 centimeters, showing the robustness of the system in a complex environment with multiple users. Instead of smartphones, the system can also locate other sources, such as this off-the-shelf BLE beacon. We believe the real-time, low-latency aspect of the system can enable numerous applications, and the signal processing pipeline can be applied to other RF protocols as well. For more details about this work, please refer to our paper.